Hi, you guys. So this lesson is on section 5.5, where we are going to find the derivatives of exponential functions that don't have a base of e, and then also log functions that don't have a base of e, right? Because in section 5.1, we saw that the derivative of natural log of x is 1 over x, and in section 5.4, we saw that the derivative of e to the x is e to the x. Okay, so let's look at, if we think about representing an exponential function with a base other than e as a to the x power, you can't use power rule. So this would be differentiating something like 2 to the x power. You cannot use power rule. And the derivative isn't like e to the x where it's just e to the x. But we can use what we know, and we can rewrite a to the x with a base of e. And the way that we could do this is by using a log property. So we can think about kind of going in the reverse of the log property that we're familiar with and rewriting a as e to the natural log of a, which we know that would simplify to be a. Okay, so we've rewritten the base of a as e to the natural log of a. And then, now that we look like we have e being raised to a power, which is also raised to the power of x, when you're raising a power to a power, you can multiply the exponents. So this expression can be rewritten as e to the natural log of a times x, where this is the exponent. And this is something that we know how to differentiate, okay? So we're going to be thinking about chain rule in order to differentiate this, where we're thinking outside function and inside function. So the derivative of e to a power would be e to the power. For chain rule, we know that we have to leave the inside alone, the inside function alone, okay? And then multiplying by the derivative of the inside, well, natural log of a is just a constant. So the derivative of natural log of a times x is just going to be natural log of a. Okay, and we're almost there. Come over here. So we have e to the natural log of a times x times natural log of a. Here's the thing. E to the natural log of a times x, that's not, I don't know, it's not very nice looking. Like technically this is the derivative, but we know from where we came from in the beginning, right? We were trying to differentiate a to the x, and we used e to the ln of a in order to be able to differentiate a to the x. But we can also go back and rewrite that as a to the x. Just to do this in 2 steps so that everyone can see it. So what I'm doing is I'm rewriting e to the ln of a times x power as e to the ln of a raised to the x power, so that I can go back to rewriting this as a to the x times ln of a. So that's the derivative of a to the x. So for example, if we wanted to differentiate 2 to the x, like I mentioned in the beginning, the derivative of 2 to the x is 2 to the x times natural log of 2. And this works also for e to the x. Like this rule still applies for e to the x. Like if we were differentiating e to the x and thinking about applying this same formula, we would have e to the x times natural log of e. Well, natural log and has a base of e, so that would actually just simplify to 1, leaving us with e to the x, which is what we already know. Okay, so we're also going to be looking at finding the formula for the derivative of a log with a base that's not e. And to do this, we're going to use another formula that we're familiar with. So log base a of x, we can actually rewrite using change of base formula. Remember, change of base formula just says that we can rewrite log base a of x as log base b of x over log base b of a. You can basically choose what the base would be. So I'm going to choose that base b to be base e, since we do know what the derivative of log base e is, right? Natural log of x. So I'm rewriting log base a of x as natural log of x over natural log of a, which, just like we did above, ln of a can be treated as a constant, or actually 1 over ln of a. I can treat as a constant so then whenever we're taking the derivative, we're really just taking the derivative of natural log of x, which we know is 1 over x. So we'd have 1 over ln of a times 1 over x, and that's it. One over ln of a times x would be the derivative of log base a of x. Just let me put an example here. So for example, if you were wanting to find the derivative of log base 3 of x, that would be 1 over natural log of 3 times x. You could also think about rewriting log base 3 of x as natural log of x over natural log of 3, and then differentiating from there. But for some of you, it might be faster to just have the formula or know the formula. So let's summarize. We know that the derivative of e to the x is e to the x. And we know the derivative of natural log of x is 1 over x. And now we know that the derivative of a to the x will be a to the x natural log of x. And the derivative of log base a of x would be 1 over ln of a. Oops, my n didn't really look like an n. Ln of a times x. Okay, so we're going to use these differentiation formulas now. Before we do that, we are going to also think about integrating a to the x. Okay, so in order to integrate a to the x, we're going to use the same strategy that we did above. So we'll have the integral of a to the x dx, and we will rewrite the base of a as e to the ln of a, and then that's raised to the x power, so we'll have times x dx. And now this is something that we know how to integrate. We can think about doing a u substitution. I'll do my side work for the u substitution up here. Let's let u equal to natural log of a times x. So du over dx would end up being natural log of a. Okay, so that means that dx is going to be equal to du over natural log of a. So rewriting the integral, we would have 1 over natural log of a, which I can pull out, times e to the u du, And we know the integral of e to the u is e to the u. So that would be 1 over natural log of a times e to the u plus c. Substituting what we let u equal to back in. So we have the 1 over natural log of a, e to the natural log of ax plus c. And then again, we remember that this simplifies to just be the base of a. So the integral ends up being a to the x over natural log of a plus c. I should be consistent. You don't technically need the grouping symbols around the a, but since I did it in with the one step, I'll do it everywhere else. So that would be the integral of a to the x, would be a to the x over natural log of a. And we'll use that here in a minute. Let's first look at taking the derivative of some exponential functions and log functions that have a base other than e. So to find f prime, this is 2 to a more complicated power. So like we saw that the derivative of 2 to the x was natural log of 2 to the x. So we need to think chain rule here, because this is a little bit more complicated, like 2 to the power is the outside function, and then the x squared plus 1 being the inside function. So thinking about the derivative of the outside function, that would be 2 to a power ln of 2, right? 2 to a power ln of 2. And then leaving the inside alone because we're doing chain rule, and then times the derivative of the inside. And that's it. Now we could clean this up. I would probably, I don't know, I guess pull the 2x out front, and then maybe the ln of 2 times 2 to the x squared plus 1. It's kind of whatever your preference is based on the commutative property and multiplication. Okay, and then you could always pause the video and try this on your own and then see if we get the same answer. Okay, so for finding h prime, the derivative of 3 to the x would be 3 to the x natural log of 3. Okay, and then you have options. I think it would actually be less complicated to leave 4 log base 2 of x as is, okay, instead of unplogging. I would leave the 4 there because then the 4 will just hang out, or I can put the 4 actually in the numerator, and then the derivative would be ln, so 4 over ln of 2 times x. And that's it. No chain rule needed for that one. Okay, oops, didn't mean to do that. All right, this one looks a little bit more complicated here. So let's choose a different color. Green. Okay, so g prime will be 5e to the x, and then we need to use product rule. And we could leave the 3 factored out, or we can say that that's one factor, that's the second factor. So maybe I'll do that. So first factor for product rule times derivative of the second factor would be 1 over natural log of 3 times x, okay, plus the second factor times the derivative of the first would be 9x squared. And this can be your free response answer if you wanted to simplify it a little bit more. I don't know, 5e to the x plus, if we had 3x cubed over natural log of x, we could think about canceling one of these x's so that we would actually have 3x squared over natural log of 3, and then plus 9x squared times log base 3 of x. For this next one, you could leave as is, or I think it would actually probably be easier so that you're not having to think chain rule multiple times, to plug and bring the 3 down in front here. So 3 times log base 2 of 3x minus 2. So k prime would be 3 times, and that would be 1 over ln of 2. Now, when we leave the inside alone, that means that the argument down in the denominator will be 3x minus 2, and then multiplying by the derivative of 3x minus 2 would be times 3. So this ends up being 9 over natural log of 2. I'll just leave factored out, of 3x minus 2. And then let's look at some indefinite integrals for exponential functions that have a base other than e. So remember, this is the formula that we're using. The integral of a to the x dx is a to the x over natural log of a plus c. Okay, so this one we would need to think about doing a little u sub. This is one that you could probably do in your head. But du over dx would be -1, so negative du will be equal to dx. So I'll have -1 times the integral of 2 to the u du would be -2 to the u over ln of 2 plus c, and then substituting the negative x back in. And if you wanted to rewrite that without the negative exponent, I guess you could always move 2 to the x to the denominator, although I think for exponential functions, it actually kind of makes more sense to leave the exponent where it is. Okay, so this also looks like a u sub problem. Let me switch colors here. We don't know how to integrate this without doing a u sub, so I'm thinking let u equal to the denominator, and then to find du over dx, we will have to use the formula. We're going to have to think chain rule, so it'll be -4 to the 2x times ln of 4, and then times the derivative of 2x would be times 2. Okay, and I need, so rearranging things here, dividing, I'm going to think about dividing by negative, or actually, I could rewrite this as I can unplug here and pull the 2 up, so that I can think about rewriting this as du over negative ln of 16 equals to 4 to the 2x dx, so that I can think about replacing the 4 to the 2x dx and I would have negative 1 over ln of 16, which you could have left as negative 2 ln of 4, times the integral of 1 over u du. Negative 1 over ln of 16 is just treated as a constant, so that will be times ln of absolute value of u plus c. And then substituting what we let u equal to back in, that'll be ln of absolute value of 1 minus 4 to the 2x plus c. The absolute value bars would be needed there. Okay, also throwing some trig into this one. You could pause and try this on your own and then check your answer with mine. I'm thinking that exponent of sine of x is what I'm going to want to let u equal to here, because then I would know what the integral of 3 to the u would be. And I know that the derivative of sine is cosine. So du can be equal to cosine x dx, which is nice. So this just ends up being rewritten as the integral of 3 to the u du. So using that formula, that's 3 to the u over ln of 3 plus c, and then just substituting the sign back in. Okay, and then we also have a definite integral, so we're going to need to think about new limits of integration. Again, if you want to think about pausing this and trying it on your own. So the first thing that I think I want to do, especially since they have different bases, this is a sum, the integrand is a sum, and they have different bases, like different exponents. I'm going to split this up. I'm going to use that sum and difference property of definite integrals and rewrite this as the integral from 1 to 3 of 4 to the x plus 1 dx plus the integral of 1 to the 3 2 to the x power dx. Okay. And the first definite integral would require a u sub. The second one wouldn't. So I'm going to let u equal to x plus 1. So my new, in just that first integral, the new lower limit would then be 2, right? 1 plus 1 is 2. The new upper limit would be 4, okay? Du over dx is 1, so du equals dx. So then rewriting this as the integral from 2 to 4 of 4 to the u du. And then this is still the integral from 1 to 3, 2 to the x dx. Okay. So the integral of 4 to the u would be 4 to the u over ln of 4. And because I found the new limits of integration, I don't have to think about substituting the x plus 1 back in. And then the integral of 2 to the x would be 2 to the x over ln of 2. With the other limits of integration. And then we can just apply first fundamental theorem of calculus to both of them. So 4 to the 4th over ln of 4 minus 4 squared over ln of 4 plus, okay, first fundamental theorem of calculus, 2 cubed over ln of 2 minus 2 over ln of 2. And then you could simplify from there, especially because we do have common denominators for both of those differences, but you can simplify or leave as is if it's for your response. Okay, so that's it for section 5.5. We have introduced these new formulas. Okay, so for differentiating a to the x, an exponential function in the form a to the x, or a log function with log base a of x, so base other than e. And then we've also found integrating a to the x. In this class, you will not learn how to integrate log base a of x. That's something beyond this class. Okay.